Okay, I heard that the link is not working. The sentence link. Okay, I'll fix this link today. And all these things will get clear when after this class.
If we have the CentOS from the previous semester, will it still work? Or do we need to like download your version?
Previous semester is which semester?
Last semester?
Spring?
Yeah.
I'm not sure. I don't know yet. I have to see. I have to look at it.
Are the assignments that are up right now the ones for the summer semester, or are these just previous assignments from?
This is for the summer semester.
Okay, so these are our assignments.
Yes, these are your assignments. So what happened is these are from summer 16, but these have been modified from, so Dr. Bazzi and Adam Duke, they use lot more assignments, like 5 or 6 assignments I think. But in summer you cannot do all those. But what I have done is I have taken some of the assignments, combined them. Some are some aspects I have deleted, some aspects I have combined. So these are tailored for the summer course. So it's more manageable, like you can finish it in 1 month. So although you have 3 assignments, but these are equivalent to 4.5 assignments for the spring semester.
So when is the first assignment due?
It will be around July 15th. I'll let you know today. After I update the link. Any other questions?
For the homeworks that you have on here, are those for this semester?
Homework is those homeworks are for your examples. You can start working on them as examples. I'll update the homeworks and post new ones. Anything else? Okay, so let's start this class. So we saw that last class what we discussed was yes. So last class what we discussed was how we can go from a high level language. We have written a program in a high level language. How we can go from there to assembly level and run a program. That is what we discussed. And we said that we are only going to focus on the compiler. So that is the first step of the entire program execution. So we are only focusing on the first step. So now the first step of a compiler is lexical analysis. And we kind of hinted at what a lexer does. Do you remember what a lexer does?
Puts things into tokens.
So it takes a program written in some high level language which is maybe closer to English, and it gives you tokens. That is the function of a lexer. So let's start seeing how you can do a lexer or write a lexer. So the first assignment is on that. You have to write a lexer. So you have to take a programming language, and we'll see how we can unambiguously write a programming language or represent a programming language, and how we can get tokens out of that. That is the first assignment. So first of all, in lexer we have to have syntax. Any programming language has to have syntax. So programming language must have a clearly specified syntax. That is also very important. It cannot be ambiguous. So what is in a syntax? So what the programmer can do while looking at the syntax is can understand what is allowed and what is not allowed. What can I write and what can I not write? So for example, C equals A star B. Right? That is one way of writing. C is a variable. You take A, multiply it with B. Another way of writing is C equals A dot B. Right? So what is it? Is dot a concatenation between two strings A and B, or is dot allowed for integers? A multiplied by B. So can you even write C equals A dot B in a programming language? That is what syntax looks like. So maybe you cannot even write C equals A dot B in some program. You have to write C equals A star B. So what makes sense, what does not make sense for a programming language? That is syntax. So what compilers can do, the first step of compilers, which is lexical analysis. What lexical analysis can do is it can understand programs and enforce a syntax. It can tell you that, okay, no, this is wrong, you cannot write it like this. So what is a program here? Here an input, so a program input is like a series of bytes, right? You don't really understand syntax by looking at these bytes. So from these bytes, you have to make sense of these bytes. So what you need to do is from a stream of bytes, you need to find out whether this stream of bytes are matching a syntax or whether the stream of bytes are a legitimate program or not. That is what you need to do. So how do we do that? So the first step to doing that is we must first assemble the string of characters into something that a program can understand. So from these bytes, we need to go to tokens. Tokens is what program what a machine can understand possibly, like a lexical analyzer can understand. So the output has to be a series of tokens. You take a stream of bytes and you output a series of tokens. That is the first step of the lexical analyzer. So now how do we do that? In order to do that, let's look at a language. How do we do it in a language? In English also we do the same thing, right? So in English we have some alphabets, A, B, C, D. We do not use just alphabets to talk, but still there are alphabets. So in English we have an alphabet A to Z and some expressions as well, question mark, exclamation mark, so on. But we also have words. If we don't have words, we don't understand English. He is a good guy, right? That sentence. You just don't say HEISAGOD, then nobody will understand. You have to say he is a good guy. So you have to use words. You cannot just use an alphabet. So you have a word. Well, how do you get words? How do you know that these are words?
Rules.
No, not rules. How do you, first of all, how do you know that these are words?
It's like in a dictionary.
Dictionary. You find it in a dictionary. So these words are defined into this dictionary, and they are again further categorized into different classes: nouns, verbs, adverbs, right? In a sentence, articles. Then you take these words, and a collection of words becomes a sentence. Now, not any collection of words becomes a sentence. You cannot say good is a he guy. That is not a sentence. He is a good guy is a sentence. So, words, this collection of words should follow some rules. When they follow rules, they become sentences. Right? You cannot just combine words in any which way you think of and say that this is a sentence. You cannot. So sentences have rules. Again, we combine sentences to make paragraphs. Now, if you read storybooks, if you read newspapers or articles, you will see that each sentence has connection with the previous sentence as well as with the future sentence. Right? So, future sentence has connection with the previous sentence. If there were no connection between two sentences, then that would be a poorly written paragraph. It won't make sense to us, right? So again, when we are doing paragraphs, sentences are connected to each other. So when we do that, then we can make out sense of what a person is trying to say. Same thing for a machine. For a machine also, you have to write it in a structured way. Write your program in a structured way. If you don't, if your alphabets are not combined to form words, if the collection of words do not have any rule, if successive sentences does not mean anything, then the program is in vain. There is no sense to that program. So what is the parallel to a program? We don't have words, we have tokens, right? Instead of words, we have tokens. Tokens are defined in somewhere in some dictionary, right? Now these tokens also, just having tokens does not work. Tokens should be combined in following certain rules to give us lines of code. Lines of code form a sentence, right? We just cannot have C A equal plus B. We don't know what that means. We have to have C equals A plus B. That's a rule, and that becomes a meaningful sentence. Again, when we combine sentences, we get paragraphs. In English. Similarly, when we combine lines of code, we get a program. A program should have meaning, which means it should have semantics. Program should have semantics. So yes, okay. So we'll come to that a little bit later. So what do we mean by language syntax then? So in programming languages, we also have an alphabet. Typically, we have these as alphabet. We can do A to Z. We can have curly braces. We can have parentheses. Right, many different things. So just as in English, we create abstractions of low-level alphabets. So we have tokens, right? Tokens can be double equal to, less than equal to, while loop, if conditions, can also be variables. Right? Tokens are also variables. A, B, C, those are tokens. Now tokens have to be combined, as we already said, to make a line of code. So tokens have to be precisely specified using certain patterns. So those patterns are combinations. Now, apart from tokens, we also have some things called strings. Strings are also important in programming language. So what are strings? If there are these alphabet symbols. You combine certain alphabet symbols, you get a string. So for this purpose, for the purpose of this course, we will have to define a string. What is a string? So we define a string over an alphabet sigma as a finite sequence of symbols from sigma. Now from this point onwards, it's going to be a little bit difficult. This sigma, right? It's not, I mean, apparently it will seem that it's easy. At this point it is really easy. So sigma is what? Is just a sequence of alphabets. Not sequence of alphabets, it's a set of alphabets. See, I'm already making mistakes. So sigma is a set of alphabets. What is a string? In that set of alphabets, from that set sigma, what you do is you collect some alphabets, a few alphabets, concatenate them, you get a string. So a string is defined over an alphabet. So whenever you talk about a string, you have to talk about an alphabet. So string is defined over an alphabet as a finite sequence of symbols from sigma. So string has to be finite. You cannot go on and on. It cannot be infinite set of infinite set of alphabets. Whenever we talk about strings, it is a finite set. Right? Another important concept is coming up. Epsilon. Epsilon is an empty string, an empty sequence of symbols. Now, it's very easy to confuse ourselves between sigma and the empty set. Right? It's very easy to confuse ourselves. What is the difference between sigma, no, not sigma, sorry, epsilon and empty set? What is the difference between epsilon, a set that has epsilon in it, and a set that is empty? Very simple difference. And we often forget that simple difference. The simple difference is that a set that has epsilon in it is not empty. It has an alphabet, and that alphabet is epsilon. It's not an alphabet, and it is a string which is also an alphabet. So the string epsilon is this empty string, and that is a member of this alphabet set. Right? So if I say that there is a set that has the epsilon string, that is not the empty set. Yes.
How can you have an empty sequence?
Very good question. This is a hypothesis. It is a hypothesis that we have an empty string. Now, it might not make sense to you, but it makes sense to mathematics. You can use empty string to make sense of mathematics. And we'll see how. We'll see how a little bit later. So empty string might not mean anything to you, but it is there for the sanity of the system. If you don't have empty string, then everything will fall apart. So this empty string is very important. So that's why I am stressing the fact that there is a difference between a set that has an empty string and a set that does not have anything. This is an empty set. Empty set is not equal to a set having an empty string. Right? So if you talk about cardinality of a set, do you know what does it mean by the cardinality of a set?
Number of elements.
Number of elements. What is the cardinality of an empty set? 0. What is the cardinality of a set that has an epsilon string? 1. So these are two different. Right? Now what is the significance of empty string? You concatenate empty string with another string, you get the same string back. So you have S, which is not an empty string, which is a finite sequence of alphabets from sigma, and you concatenate epsilon with it, you will get the empty string.
So, for example, in C, is the spaces, is that an empty string?
No. You will see later that you can write an entire programming language just using spaces.
But in C.
Oh, in C, no, still not. It's not the empty string. Empty string is a concept. It is a concept that helps you understand the mathematics. It's not, you don't really have it in practice. Empty string is a concept. So concatenate empty string with S, it gives you get back S. Now concatenation with empty string is commutative. What do you mean by commutative? Everybody understands what is commutative operation? Just one way and the other. So you have epsilon S is equal to S, as well as S epsilon is S. Right? So commutative. That's what you have here. Epsilon S equals S epsilon is equal to S. So what we'll do is, whenever we will talk about strings, we'll either have it in double quotes or we'll have it in italicized and dark blue color. Yes.
And we concatenate to epsilon.
Yes, that's what we did. Oh, two epsilons? Yes. What will happen if we concatenate two epsilons? Epsilon. Okay. So we have strings. Now we have the concept of languages. The language is a different concept of string. It's different from the concept of string. So what is a language? Let's define language. So sigma, we know, represents set of all symbols in an alphabet. So sigma is our alphabet set. There is symbols inside sigma. It can be from A to Z, it can be comma, exclamation mark, question mark. All these are symbols and these are part of the set sigma. Right? And this sigma, okay, we'll come to that, whatever I was going to say. We'll ask you a question. That way is more interesting. Then we define a set sigma star. What is the set sigma star? The sigma star is the set of all strings over sigma. So if let's say sigma is ABC, right? Let's have sigma as ABC. Well, what can be sigma star?
All possible combinations of A, B, and C.
Which is how many?
All possible combinations of A, B, and C.
So he says
any number
infinite.
of A's, any number of B's.
Any number of A's, any number of B's, any number of C's, right? So sigma star is that kind of a set. So sigma star contains all the strings that can be created by combining the alphabet symbols into a string, all possible ways. Now a language L over alphabet sigma is a set of strings over sigma. So sigma star was what? Sigma star is a set of all possible strings that you can create using the alphabets in sigma. What is a language? Language over the alphabet sigma is a particular set of strings over sigma. So what can you say about the relationship between language L and sigma star?
Cell is subset. Of
L is a subset of sigma star, right? So language L is basically a subset of sigma star. Now we come to the question of the cardinality of these sets. So we come to the question that is sigma infinite? Why not? Did I stop sigma from being infinite?
No. It's infinite.
It can be infinite. It can be infinite. Sigma can be infinite. But the question is it useful to have infinite sigma? Nobody uses it. In a program, you cannot. So what means what it means to have infinite sigma? It means that whenever you are writing a program, every time you will see a new symbol, right? Every time you are trying to parse or you are trying to generate tokens from a set of bytes, you can get a new token. So if every time you get a new token, you have to make sense of it. That's not possible. Every time if I get a new token, every single time I get a new token, I have to make a sense of it. That's not feasible. So sigma can technically be infinite, but there is no use to having infinite sigma. So we will focus on cases where sigma is finite. So it's a finite set of symbols. Sigma. Now we have changed the definition of sigma. Initially we said the sigma is just a set of symbols. Right? It can be infinite. But now we say sigma is a finite set of symbols. Right? That because it's useful that way. Sigma star, we already said that it can be infinite. Right? Sigma star can be infinite. Is a language, can a language be infinite?
No.
Yeah.
No, yes.
I mean, it shouldn't because it's what you can only use. Like it depends on certain rules, kind of.
Okay, let me ask you this then. You know set of natural numbers. 0 to 0, 1, 2, 3, 4, 5, 6 to infinite. Right? Do you know the set of real numbers? 0, 0.1, 0.2, 1.2, 5.36. There is a concept of countably infinite and uncountably infinite. Do you know about that concept? What is the set of real numbers? Is it countably infinite or uncountably infinite? It's uncountably infinite. The set of natural numbers is a subset of the set of real numbers, right? It's still infinite. The set of real natural numbers is still infinite, but it's countably infinite. What do you mean by this concept? Countably infinite and uncountably infinite.
1 to 1 instead of natural numbers.
Which means,
It's measured.
yes, kind of true. Which means that you can give a unique counter to every point in that set. So if you have a natural number, you can give the counter 1 to the first number, 2 to the second number, 3 to the second number, and so on. You will have a unique counter for every number. For a real set, that's not possible. How many unique counters will you have? Between 1 and 2, there are infinite number. So you have to stop somewhere. You cannot have more than infinite number of counters. So between 1 and 2, you utilize infinite number of counters. Then between 2 and 3, you have to use the same counter, because you are already into infinite number of counters. Now these kind of concepts scramble with your brain a lot, right? It just twists your brain, turns your brain. You have to think in simpler terms. So L can be infinite, or even though it is a subset of sigma star, L can be infinite. So an example is, if the natural number, right? Natural number can be my sigma star, the set of all natural numbers. L can be the set of all even numbers, right? That is on my language. So whenever a number comes, I know it's even or not. Very easy, divide by 2. If there is no remainder, then that's even, right? So I know that my language, I only speak in terms of even numbers. That's my language, and that is infinite. That language is also infinite. It's countably infinite, but still infinite, right? So L can be infinite. So L is a language, and it is defined over sigma. L is a subset of sigma star. Sigma star is the set of all strings that we can generate from the alphabet sigma, and L is a subset of sigma star. Sigma star is infinite. Sigma could have been infinite, but we limited it to finite. L is infinite. Now you can go home, right? And think about this. And not yet. So now we come to another concept called regular expressions. Regular expressions are a way of specifying rules for tokens, which means there is some rule of combining these alphabets. What rules can we come up with? So that is a part of regular expressions. So tokens are typically specified using regular expressions. What are regular expressions? They have certain properties. So regular expressions have to be compact, expressive, precise. They are widely used, so these are not the property. Easy to generate an efficient program to match regular expressions. Now, what are these terms? Compact, expressive, precise. Now, right now we have no idea, but we will have idea when we talk about the regular expression in more detail. You had a question.
I was just going to ask what the color of this mathematical compact was.
Yes. No, mathematical compact is a different thing. Compact set is a different concept. Compact set means there are no holes inside the set, but that is different. These are just English terms. These are properties of regular expressions. Why are these properties? Why do regular expressions have these properties? We will see when we talk about regular expressions. So let's talk about it. So if we want to define regular expressions, we have to learn the syntax of regular expressions. So there are certain rules for regular expressions. So a regular expression can be the following. It can be phi. What is it? Phi. It's an empty regular expression. Again, this is another concept that scrambles with the brain. So epsilon was what? The empty string. Now phi is an empty regular expression. What does it mean? How do we use it? No idea. Just wait and watch. Right. So let's say there is a phi, which we call it as an empty regular expression. Then there is an epsilon, which is an empty string. Now we have two things: empty regular expression as well as empty string. Double scrambling. A is an element of the alphabet. So alphabet is sigma, right? Alphabet set is sigma. Pick any element from that alphabet set, that becomes a regular expression. Right? Any element, A, B, or question mark, exclamation mark, that becomes a regular expression. If it is an element of the alphabet. Then, so the top three, these three specifies some initial regular expressions, right? Then we can make more complex regular expressions following certain rules. The first rule is R1 and then this bar R2. What is this bar? We don't know. We don't know as of yet. So let's say this is an expression. This, whatever it looks like, R1 bar R2 is a regular expression. What does it mean? We don't know yet. So where R1 and R2 are regular expressions. So you choose any from here, right, and put it in R1, put it in R2, then A or A bar B becomes a regular expression, right? That is one rule. The other rule is R1 dot R2. That is also another rule. What does it mean? I don't know. As of yet, I don't know. We will know a little bit later. Then another regular expression is this, parenthesis R. Parenthesis R is a regular expression, where R has to be a regular expression. And then finally R star. If R is a regular expression, then R star is also a regular expression. Right? So a regular expression defines the language. That is the set of all strings that the regular expression describes. So if you think of it, language is what? Is a subset of sigma star, right? Now if you think of regular expressions, all these, what will this regular expression result in? If bar, dot, star, all these are part of the alphabet, then what are these? These are just strings, combinations of the alphabet, right? So this is a set of strings. And this is a subset of sigma star. Whatever we can do with regular expressions. This is a subset of sigma star. So regular expression is a language. Any subset of sigma star is a language. Right? So regular expression is a language. Now, how do we define that language of regular expression? What is the language of regular expression? So we have just defined some rules. Now, what is the language? What are the strings that are included in a regular expression? So if we can find out the strings that are regular expressions, then the set of all those strings will be the language. Right? Language is what? Set of all strings, subset of sigma star, and regular expression is what? Is some rules that we have specified, which we will call regular expressions. So the set of all strings that follow regular expressions is called the language of that regular expression. Do you understand? Right? Clear up to this point. So what is the language? So first of all, L of phi. So this is phi is a regular expression. If we want to find out the language of phi, then the output is phi. So language of phi is phi. All these are abstract concepts. Might not make sense now. It will make sense when we do examples. The language of epsilon, the epsilon regular expression. That language is a set that has only the empty string. Since it is a set with a string, it is a subset of sigma star, right? It's a set with a string, so it's a subset of sigma star. Any subset of sigma star is a language. So this is also a language. L of epsilon. And that language has just a single string. That is what is happening. Then the language of A, where A is any alphabet from sigma. That language is a set that consists of only a single string, that is A. Right? Now we have defined these languages, the top three. How do you define the language of R1 bar R2? What is that language? So what we can do is, language of R1, LR1, can be any of these, any combination of these, right? The first 1, 2, 3. Now if you want to define language of R1 bar R2, then what we will say is that first try to find out the language of R1. It will be a set of strings. Then try to find out the language of R2. It will be another set of strings. Just compute the union of the two sets. That becomes the language of R1 bar R2. When we do examples, remember these simple rules. Don't just start blindly writing the set. Remember the simple rules. If you remember the simple rules, you won't be wrong. Then we define the language of R1.R2. What is the language of R1.R2? Again, first you compute the language of R1. It will be some set of strings. Then you compute the language of R2. It will be another set of strings. Then what you do is you take the concatenation of these two sets. Now, how do you do concatenation of sets? That is a concept that will come to when we are doing its examples. I can explain it using examples. Basically, what is happening is that, do you know Cartesian product of two sets? Okay, Cartesian product. What happens? That you take one element and the other element combine. That becomes one point. So all possible combinations. So that dot is similar to that. Cartesian product of the set of LR1 and the set of LR2. So these are the rules. These are the language rules. So now let's do some examples. So let's try to see the example of that rule. LR1 bar R2. So that means LR1 union LR2. So let's see some examples. Okay. So now you know small a and small b. Is small a language? Is small a regular expression? Yes. Small a is a regular expression, right? So so language of a bar b. Small b is also a regular expression. Right. So what will it be? Follow the rule. So what is the rule? L a bar b is L a union L b, right? What is L a? It's a set containing A, right? It's a set containing A, and what is L b? It's a set containing B. So you do L a union L b, you just get a set which has both the numbers or both the alphabets, A, B, right? What is this one? Can you work out this one on your own? How will you go about doing this?
You would have LA union LB union LC, which would then be either the set with A, the set with B, or the set with C, which would then ultimately be a set with A, B, C.
Yes, correct. But if you think like that, then it might lead you to problems. Don't jump steps. So first of all, take one operator at a time. Now he is correct. He said A, B, C is perfectly fine. But when you go to complex systems, it might be a bit tricky. So go one by one. So A bar, B bar, C, right? How can you divide this? You can say that A bar B is R1 and C is R2. A bar B is a regular expression, right? C is also a regular expression. So I will only focus on the rule. The rule does not tell me to compute 2 bars. The rule just has 1 bar. So I will apply the rule. So I have to convert this expression into an expression which has just 1 bar. Because I don't understand 2 bars in that rule. There is no 2 bars in that rule. So I have to convert it in that way. How do I convert it in that way? I say that A bar B, that is one regular expression, and C is another regular expression. So R1 is A bar B, R2 is C. So in that case, what I do is I go to the next step. That L of R1 union L of R2. That's what I know, right? I can apply that rule. Now what is happening is that I know L of A bar B. A is R1, B is R2. I know how to do that. I know the result. It's A comma B, right? So I put that. So which means that now I have A comma B union C, right? These two sets. So the final set becomes A comma B comma C. This is the same answer that he said. It's correct. But I would suggest doing it in this way. The moment you try to break away from the rule, it can get you into corner cases where you might be wrong. Right? So directly, blindly, whatever expression you get, you try to fit into one of the rules. Right? And the rules does not say 2 bars, it says only 1 bar. So you have to find out a way of dividing this expression where you can literally apply the rule. Right? What is this say? It's a set containing A and epsilon. Is it the same as language of A? LA?
No.
Why not?
Because epsilon is a separate string.
This is not same as LA. This set is A comma epsilon. Whereas LA is just A. It does not have the empty string. The cardinality of LA bar epsilon is 2 and the cardinality of LA is 1. So these are two different sets. Do you have a question?
The set with nothing in it.
Which one?
That set with nothing in it divided by the set with the other string.
No, that's what I said. A set with nothing in it is not a set with at the epsilon string. A set with nothing in it has cardinality 0. A set with the epsilon string has cardinality 1. So totally different sets. Right. What is this set?
Just epsilon.
Just epsilon. Right. Even if it's epsilon comma epsilon, it's the same element. If it's the same element, you don't need to repeat it. So this is just epsilon. And as I have been saying, this set which has epsilon in it is not the same as an empty set. This you have to remember all the time. Very important assumption. Now let's understand R1 dot R2. For two sets A and B of strings X, Y. Okay, so if let's say there is a set A and there is a set B, what is the set A dot B? It is basically the concatenation. So take an element from A, take an element from B, concatenate. Right? That is A dot B. So whatever you get is what you get. So let's see some examples. Yes. So A is a set which has AA, comma B. Right? AA is one element. It's not two elements. So cardinality of set A is 2, and that of B is also 2. Right? So set A has AA, which is a string, and B another string. Set B has small a and small b as two separate items. What will be A dot B?
A, comma, B.
A, comma, B, and that's it?
A, B, B, A, B, B.
And AAB.
Yeah.
AAB he already said. So what? AAA, AAB, BA, BB.
So it's the combinations of it.
Yes. Will you have BAA?
No, it's not. We are
Because the definition of A dot B is you first take an element from A and then concatenate with an element of B. So element of B is always after. Right? So you cannot have BA. And for the same reason, you cannot have AB. Right? Now, what is the concatenation of this? Or A dot B of this? So A is now has the empty string, and B has A comma B. Now you see the beauty of why we have empty strings.
It should just add A and B to the previous example. Because when you concatenate directly on, it's just A.
So what he's saying is that it will just add A and B to A dot B. Why? Again, concatenation is what? You have to take an element of A and put an element of B after it. So if you have just that empty string, so you can have empty string, comma, empty string A, empty string B. And if you concatenate with empty string, what happens is you just have A and B. Right? So this set is now different. It has A, B, B, but also A and B. So that is what, if you had just said that, oh no, this is empty string, so that means it's nothing, just omit it, you get the same A dot B as the previous one. That is wrong. You have to have the empty string. If you have the empty string, then A dot B is different from what you had previously. Now you have A and B as well. So keep in mind, empty string is different. It's not the same as empty set. Right? Now we have to define some operator precedence, because we can have expressions like that. A or B dot C. This can lead to ambiguity. You can either consider it as A union B dot C, which means like this. You can either have A union B, you do that first, and then you do dot C, or you can also have A union. So you first do B dot C, and then you union with A. So which one is it? So you have to define some precedence. So if you talk about arithmetic, A plus B multiplied by C, how do you parse it? Multiplication first. You say that multiplication has precedence. So if you say 2 plus 3 multiplied by 4, the answer is not 20. The answer is 14. Right? So you first multiply 3 by 4, you get 12, and then you add 2 to it. Not the other way around. You don't first add 2 and 3 and then multiply 4 to it. No. So just like mathematics, we have to define precedence. Yes.
You don't need to have operator precedence. You can have notation, right?
Pardon?
You can have notation that doesn't require operator precedence.
No, it was still require operator precedence. That one, right? A or B dot C.
You can define notation that doesn't require it.
What do you mean? What notation?
You define the notation so that you don't need operator precedence. It's always in the
Yes, for example, that notation, right? The second notation. If you have properly placed parentheses, then you don't need. Is that what you are saying?
Sorry.
I think it means that whatever order it's already in
Yeah.
is the precedence that you have.
Oh, whatever order that's one issue. That's one way that you can go. Yes. So you parse from right to left. Whatever operator you get first, you use it. That is one way to go. That is again another precedence. Precedence is whatever comes first. That is the precedence. So there can be different ways of defining precedence, but here what we'll do is here we'll consider that star is higher than plus. So that means dot has a higher precedence than or bar. So in here, so how will we parse this then? Dot has higher precedence. So how will we parse this?
LA union L B dot C.
Yes. So here we will have two regular expressions. R1 is A and B dot C is R2. We will first have to compute B dot C. So that means we will divide it like this. LA union LB dot C. And what will happen is B dot C is what? It's just simple BC. It's simply BC. So A union BC. So this set becomes A comma BC. Right? Any doubts about this one? Okay. When does this class end? 11, 20 or 30?
30.
30. Right? Okay. Another trivial thing is that if you have parentheses around a regular expression, then L parenthesis R is same as L. Right? That's what will happen. Then we have this example. So what will be this? What will the output of this one? What is the language? How will you divide this?
Language of A bar B. Language of C.
L bar B is R1 and R2 will be C, because now you have put parentheses around. So this will be like L A bar B dot L C, and that is A bar B is A comma B, and you do dot C of it. So the result will be AC comma BC. Right? Now we come to a very confusing concept: Kleene star operation. So we want to find out what is the language of R star. What is the language of R star? So the rule is this: the following. R star will definitely have the empty string. The first thing you should do if you want to evaluate language of R star is blindly take the empty string, put it into the set. Then what you do is you calculate the language of R. You calculate language of R, put it into the set. Then you calculate language of R dot R. Language of R dot R, put it into the set. Then you compute R dot R, put it into the set. Keep doing it infinitely. Then you'll get the language of R star. So that is the Kleene star operation for regular expressions. So we'll see some other notations. So L0R, right? What is L0R? L0R basically is the empty string. Then LIR becomes Li minus 1R dot LR. And what is L star? L star is the union of all LIRs. So this is like a recursive definition of the Kleene star operator. So what is the definition here? So we first say that, okay, let's define a new variable called L0R. What is L0R? L0R is the empty string. Then we say that what is LIR? LIR is basically you calculate first you calculate Li minus 1R. and then you concatenate it with LR. So if I is 1, if I is equal to 1, L1R, L1R is in concatenating L0R with LR. Right? So which means the empty string, comma, whatever is in the language of R. So let's see an example. So we want to do LA bar B star. How will we divide this? Here.
Give us the definition of I one. So I doesn't need to be in situation. I is just I has to be an integer.
Yes. I is an integer. Any other doubts? We'll see an example, it will make it more clear. So we want to find out this A bar B star. How do I divide this?
So it should be empty. So epsilon
No, wait.
A
Go step by step. Follow the rules.
dimension A bar dimension B star.
Not bar. When you are talking about language, there is no bar. There is union.
Yeah.
Regular expressions have bars. That is regular expression. When we are in language domain, there is no bar. I cannot use bar operators on languages. This is a very important distinction that you need to understand. Whatever operators I use on regular expressions, I cannot use on languages because regular expressions are different from languages. Languages are set of strings. Regular expressions are not a set of strings. It's something else, something we don't know what it is. It's just some R's and A's and B's. Right? So regular expression is not a set. So whatever operation, the bar operation, dot operation, star operation that you are doing, cannot do it on languages. For languages, you have separate set of operations. You have union, you have concatenation. Right? So you have to say in terms of that. So LA bar B star means LA union L of B star. Right? So if you do that, then what happens? What will be the set? What is L B star?
Epsilon.
You have to have epsilon, so you just blindly put epsilon in it. Then you have to union it with L of B. What is L of B? B. So you have epsilon, you have B. Then you have to union, compute the union with L of B dot L of B, which means what is that? BB. That is the set that has BB. Then LB dot LB dot LB. That is BBB. So what you have is this: A comma epsilon comma B BB BB and so on. What is this one? Epsilon, yes, first of all you have to have epsilon. So here what you have is A bar B is your regular expression, right? A bar B is the R, and you are computing LR star. So what is LR first of all? R is A bar B. So what is LR? A comma B. Right? You have, so LR is A comma B. So if you have that, so first of all you blindly put in epsilon, right? Then you union with LR. So LR is A comma B, right? Then you do a union with LR dot LR. So A comma B dot A comma B. What is it? AA, AB, BA, BB, right? Any doubts? LR was what? A comma B. So LR dot LR is what? A comma B dot A comma B. What is the set? Combine A with A comma B and then B with A comma B. So AA, AB, BA, BB, all of that. Then you want to do union LR dot LR dot LR. What will that be? So basically this one, dot A comma B, not the other way around. This one dot A comma B. So what we will have AAA, ABA, BAA, BBA, then AAB, ABB, BAB, BBB.
Just dot operator completely.
No, dot is not coming. So you have this AAA, AAB, ABA, ABB, then BAA, BAB, BBA, BBB. Right? Then do you want to go to the next step? That's not. So that is the R star, language of R star, in R star. Yes.
The next step though would be taking that and then put AB.
Yes. So now let's come to the concept of tokens. So tokens can be letters, right? It can be letters as A, B, C, D, capital A, capital B, capital C. It can be digits, 0 to n. It can be IDs. ID is what? ID is a word. So ID, so these are all regular expressions. And we are now writing regular expressions. So we are defining tokens using regular expressions. So first the letter, this is a regular expression. Digit is a regular expression. Now we have an ID which is a regular expression. This is a kind of a complex thing to understand right now. Right? So what is the regular expression? Letter. Then we have parenthesis, letter, or a bar, digit, bar, underscore, star. Now note that here we have omitted the dot sign. There is a misuse of the regular expression. But in the course of this class, we will allow certain misuses of terms because writing dots and star and bars becomes a little bit difficult after a certain point. So this is a misuse that will allow. You can omit the dot here. So you have letter, then letter, a bar, digit, bar, underscore, and star, right? That is your ID. So what can be the possible values of ID? So let's say, is this an ID?
Yes.
Yes.
Why? Why is this an ID?
Has a letter underscore.
So what the,
And it's some sort of letter.
okay, so is this an ID?
No, because this is not a letter.
That's not an ID. Right? Because it does not, the ID has to start with letter. And then after that, it can be just epsilon, or it can start with either a letter, or a digit, or underscore. Does not matter. Now the question is, how do we define a number? So we have a digit, we have defined a digit, right? We have defined a digit, but we need to define a number in 23.66. How do we define that? Using regular expressions. So if we just define it like this, a number is equal to digit star. Will that work? Let's see whether it works or not. So will this be our number? Digit star? Yes, this is a number. This one?
Yeah, in the language defined, yes.
In the language defined, this becomes a number. We don't want this to be a number. So we have to enforce that it has, the number has to have a digit. Right? How do you enforce that?
Okay.
With a digit.
Number.
Yeah.
So what we do is this. Digit, digit star. Right? So in this case, we have 132 as a number, right? Will epsilon be a number? No, because we are forcing a digit. 0? Yes, because we have 0 and a digit. 0 is a number. This one?
access it is fine.
That is also termed as a digit or a number. But that is not useful. We don't want this to be a number. The same as 0. How do we get rid of this?
You omit the 0 in the first digit.
If you omit the 0, yes, you omit the 0 in the first digit. No, if you omit the 0 in the first digit, then you will not have 0.
So you'd have 0 or, and then you'd omit the 0 in the digit, first digit, and then you do digit.
Something like that. So what you do is you define another regular expression. You define another regular expression, call it p digit, short form of positive digit, right? So in here you say 1 to 9, that is p digit. Now then in num you say p digit star, but this does not work because you have 1, 3, 2 that you can express. Can you express 0? You cannot express 0.
0 or p digit star.
Pardon?
So be 0 or p digit star.
That is one way that you can do. Before coming to that, you cannot express 0, but you also avoid this, right? You also avoid this. So what you can do is what he suggested, that you can have p digit dot digit star and then OR it with 0, right? So in this case, can you have 1, 2, 3? You can. Can you have 0? Yes, you can. Can you have 0, 0, 0, 0? No, you cannot. Can you have this? No. So we are good. So number will if it is an integer number. So now you cannot do real numbers yet. Right? You cannot do real numbers. Integer numbers you can express it like this. Now how do you define a decimal number? So for a decimal number, what you need to have is you need to have a dot somewhere in the alphabet. So what we say is that okay, so decimal number is num concatenated with dot concatenated with num. Now why do we have that weird expression slash dot? Because dot is same as the concatenation operator, right? So whenever a symbol is same as an operator, we will use the slash sign just before the symbol, right? So slash dot means dot is a symbol in this case. Okay. So that is what this. So if you have this decimal equals num dot slash dot num, then is this our what was num? Oh, num was this p digit star or 0, right? So now we are using the num. So 1.5 is it the decimal?
Yes.
Yes, it is. 2.10.
Yes, also, yeah. Num can be 10.
Is it 10 or 0? Oh, no,
It,
10.
it should work.
It should work. It should work, right? 1.01?
No, not that one. Num starts with a constant. P digit.
Wait, no, num can be just 0,
But it can't be.
but it cannot be 0, 1.
Yeah.
Right? So 1.01 does not work. So you have to change. So what if we have this decimal equals num and then dot digit star?
And you can have an epsilon, and you can have.
You can have an epsilon, but then what will that be? So 1.5 you have, right? Fine. You can create that. 2.10 you can also have that. 1.01, yes, you can have that. But you can also have this. 1 dot. Right? That's what you are saying. But this is not a decimal number. What if we have this? Num dot digit star.
We can end with multiple zeros. I don't know if that's alright.
Yes. But that is fine, I guess. So you can have 1.5, you can have 2.10, 1.01, you can have, can you have one dot? You cannot have one dot because you have to have a digit. Can you have this? You can have this. Do you want to have this? You don't. You only want to have 0, right? So it will be your homework to find out if there is a representation that avoids this. Right? We won't discuss this in class. So now you have these tokens. This is how we can define tokens using regular expression. So what is the job of a lexical analyzer? A lexical analyzer takes this series of bytes that are programs, right? So programs also you have to input as bytes. Everything is bytes. Even if that is a string, it's bytes for computers. There's a series of bytes. You take this series and you output tokens following the regular expressions. That is the functionality of a lexical analyzer. That is your first assignment. You will be given a regular expression, a way of expressing the program. You have to run the lexical analyzer. You will be given a program as input. You output tokens. That is the first assignment. And I'll update the OBA files and whatever. So during the weekend, what you can do is you can set up the environment. On Monday we will discuss the assignment. Okay, so the API that we will discuss in class will refer to the lecture as having a function called getToken. So this getToken, what it does is that it reads a certain amount of data from the file and converts it into series of tokens. So specifically it reads one line, takes one line and gives you out the tokens. So getToken function is what you have to implement. So tokens are specified using regular expressions. So this is the pictorial view, whatever you get. So you have a source file which has a program. You input it to the Lexer gives you num, ID, operator, ID, decimal, and so on. Right? Every time you call to getToken, it gives you one token. The next one. So now let's say we have this is a regular expression, right? Expressing tokens. Now let's see some example. So when you call getToken, what do you get? Right? So what token does getToken return on this string? So this is a string. You have to tell me all the tokens that this getToken will return on this string. So what we will do, and we'll see a rule that we'll follow. But before we see that rule, intuitively what happens? What should happen?
So it's gonna give decimals.
Pardon?
Read the first token.
So what is the first token?
It'd be none because it's just one, right?
Okay, num. Then
And then which first will be done. Well, anything.
so what are the sequence of tokens? Just tell me the sequence of tokens for this particular string. That should happen. That should come out.
Decimal ID decimal.
Yes?
Decimal ID decimal.
Decimal ID decimal. So he says decimal ID decimal. Yeah.
ID dot num.
ID.
Yeah, I think it's the biggest one, right? Because ID could be.
So many different
Oh,
ways.
never mind. There's some letters. So. That's
So first of all, do you get num? Will you get num? Yes?
Yeah.
Will you get num as a token?
Yeah.
No.
No. The first token should be a decimal. Because that's the largest string that matches regular expressions. Right? So, will you get ID?
Yes.
Next one might be ID. Right? So you have to follow certain rule. I just said that the largest one that matches the regular expression. What is that? That is the rule, right? So you have to follow certain rule. So what is the rule? The rule is called longest matching prefix rule. Longest matching prefix. So we will follow certain rules. So what is that? Starting from the next input symbol, if you just started reading this string, then it is the first input symbol. So starting from the next input symbol, find the longest string that matches its token. So you start from the right, no, left, sorry. You start from the left, go towards the right, whichever matches. The longest prefix that matches, longest string that matches a regular expression. So break ties by giving preference to token listed first in the list. So there might be multiple tokens that match, right? So you have to break ties by just following the order. So if you say that okay, ID matches, there was a token that matches both ID and dot. If you just have a string dot, it will match both. No, it will not match later though. It won't match ID. Let's assume, I'm assuming here. Let's assume that, no. Let's take an example of 2. There is a string 2, right? It will match both num as well as decimal. But what you return is num because it's listed first in the list, right? So that's the longest prefix matching rule or longest matching prefix rule. So let's take an example. So let's take this example 1.1 ABC 1.2, right? So initially what you have to do is you look into all the regular expressions and say what does it match. So initially your header, because you have to have a header while you're reading, your header is nothing, 0, right? It's not even the empty string, it's just nothing. So in this case you say that potentially it matches all of them. You don't know yet. Potentially it matches all the rules. Then you take the next symbol. This is what? This is a p digit, right? So this is a p digit. What does it match immediately? Immediately it matches what regular expression? If you go here, to have a num, you just need p digit. That's it. Because the rest is digit star, so it can be empty string, right? And the or is 0. So if you don't have 0, then that's fine too. So it immediately matches num, perfectly matches num. But potentially it matches decimal as well, right? Potentially it matches decimal. So what you do is you list all these. So it matches num definitely. It potentially matches decimal. Now since it's matching num now, it is also potentially matching num. Right? So you say that okay, potential is decimal as well as num. Then you apply, then you in another table or in another column, you keep what is the longest match up till now. The longest match is num, right? There is the perfect match, and what is the length of the match? 1. That is the first symbol that we read, right? The longest match is num, length of the match is 1. Are we out of time? So we will continue from here.